we would like to find the area of a surface in 3 dimensions. Now, picture that we have z equals f of xy, and when I project it down onto the xy plane, this would be our region in the xy plane. Now, in order to find the area of the surface, the simplest way is to imagine we split it up into a whole bunch of really small parallelograms on the surface, but then when I project that parallelogram onto the xy plane, I get a very simple shape here, delta xi in this direction, delta yj in this direction, and the area of this piece, which we will call the ijth area, is simply that product. I can use that to find this area rather easily, but this area can't be this area, so a simple way to think about this is if this represents this piece right here in 3 dimensions, I need the area of this. But when I project this down to the floor, I will get a smaller region because of the angle that this has. So what we need to do is figure out how to multiply this by the appropriate value to get this area. And the easy way to do that is to look at the partial derivatives. So if I think of this as a vector, that piece right there, we'll call it vector A, and that piece right there as vector B, then what I'd like to do is vector A lives on the xz plane, vector B lives on the yz plane. So all I really need to do is look at the slope. So if I'm looking at the xz plane, then I know the slope is the partial with respect to x. And that would simply be delta zi over delta xi. If I'm looking at the yz plane, I know that slope is the partial with respect to y, which would be delta zj over delta yj. Think of this like rise over run. So from that standpoint, that would mean that delta zi equals fx times delta xi. Delta zj would equal fy times delta yj. And now we can easily describe the two vectors A and B. Vector A, which lives entirely on the xz plane, would be delta xi, 0, because there's no y component, delta z. But we just saw that the delta z would be fx delta xi. And then vector B, there'd be 0 on the x direction, delta yj, and then delta zj, which we just saw here, is fy delta yj. Now let's continue from this point. Now, in order to find the area of this parallelogram, all we actually have to do is find A cross B and take its magnitude. So now that we've established what A and B are, then A cross B would simply be this. So negative fx delta xi delta yj, negative fy delta xi delta yj, and finally just delta xi delta yj. You notice we can easily factor out the delta xi delta yj term, which would be positive. Therefore, the magnitude would be, I'll factor that out first, that would be the sum of the squares of what remains. Inside the square root, so I have fx squared plus fy squared plus 1. This is called the surface area parameter. So now if we take the Riemann sum, if I said let's add up the double sum over all the i's and over all the j's, that would establish now an integral. And the integral for the surface area would be the double integral, again, over the region in the xy plane, because we are integrating over x and y, of the surface area parameter dA, choosing the order dy, dx, or dx, dy based on the region described. Now, it turns out this is all we have to do to set up a surface area problem. So if I knew how to find the area of the region, all I do now is add this particular integrand. Now what you'll notice in many cases, because of the form of this term here, you might find that polar makes it easier depending on the region, again, and depending on the integrand. But now for all surface area problems, where I define it in this way, I can go directly to the answer. So now if you look on Canvas, I've posted several examples under the notes section.